Thank you so much for the invitation to present some of our translational research, which is obviously a little different than what we have been talking about for the rest of the meeting, but I think stays in line with your goals of functional preservation and minimally invasive surgery. So we're talking about microrobotics today, and I am a tumor person, so of course I always think of tumor applications, but obviously there are many neurosurgical applications potentially for this new platform technology. So as we know, there's a lot of robotics moving into neurosurgery. We see it here at this meeting. And particularly for cranial surgeons, the question becomes, can we move beyond just stereotaxy in our robotics, as particularly in cranial neurosurgery, and move on to something that is more meaningful, whether it's whole tumor resection or just addressing more complex robotic functions. And so the way that our group sort of thinks about robotics and neurosurgery, and I think the medical microrobotics field thinks of it, is in a couple ways. And so the first you can think about robotics is, of course, in size and scale. And so if we break down robotics into these areas, we know that we work with macro robotics in the OR, and there's been a lot of nano research, but there's this open area within medical application of robotics, and that is in the micro scale, so a centimeter or less. And this is where our group focuses. And this is relatively underdeveloped, potentially highly impactful within neurosurgery, given the scales at which we work. The second area of robotics that is growing and developing quickly is, of course, what we make our robots out of. And while we have always traditionally sort of made our clinical robotics out of hard materials, and we think of the traditional robotic arms that we see out there in the presentation area, there's actually a big move towards smart robots, or what we say is soft robotics, or a combination of the two materials, which is particularly applicable when we think of robots at the scale of a micro scale. And the last thing, of course, is always in engineering is control. How much control is afforded to the device versus the surgeon? And obviously there's a lot of controversy within this, but I think generally within medicine, we always think of surgeons somewhere in the loop, right? How much in the loop is hard to say. So our group focuses on specifically microrobotics, as I have alluded to, which has a particular number of advantages for neurosurgery. Particularly, these are very small robots. They're a very rapidly expanding field of engineering, and they have a few helpful possibilities for neurosurgery. They are untethered. They allow us to be particularly very precise, which can be a challenge with our current robotics that we use in the operating room. And of course, they are extremely small, much smaller than what we currently use. This was actually an example, it's large scale, obviously, of another feature that's very interesting within microrobotics is that they can work together cooperatively as a swarm. So you see here, these robots are working together to be able to move the cell phone across the table, right? So that's an example of swarm robotics, which microrobotics can do. So we obviously know as a group malignant brain tumors, and that's what our group focuses on currently from a platform technology development standpoint. And so we started out actually trying to use ultrasound, which is another technology that people in this group are very interested in, as a way to actuate and move our microrobotics. And we did that for a couple of years, and then we realized that quickly that was actually not a feasible way for us, particularly to be able to move within the brain soft tissue, which is what our goals was, and then within the CSF space. And so instead, we moved to magnetic actuation, and that was one of our first microrobots that we developed. We create micro drillers within the medical microrobotic field. That's our niche area of expertise. And it's exactly as the name implies, something that drills through the tissue. And that was our original setup, as you can see there, to work on large animal brain tissue. And we used a Helmholtz coil at that time. And so our current solution, at least from a micro driller perspective, is what you see here. We are able to parallel process these micro drillers. They are essentially 3D printed with very complex biocompatible materials. And then there's a magnet, as you can see on there. One of our current applications is for targeted drug delivery, which we'll talk about. And for that, we use, as you can see there's the driller, the hydrogel payload, which is how we deliver our drug, which is in the form of nanoparticles, and then the magnet, which allows us to be actuated. And our microbots are able to obviously move on the surface, most importantly, drill effectively through the brain, which is actually quite challenging at these scales, and then swim through the cerebral spinal fluid. You can see this relative size compared to Lincoln's face on the penny there, and then a schematic of our overall clinical setup. So whenever you think about developing a new platform technology, we obviously, from an engineering perspective, need to think about how we fabricate our particular, microrobots of interest and for their particular application, how we actuate them, which is of course, our magnetic system, and how we control them. And we'll talk about the imaging that we use to control ours. So we'll start first with fabrication. This is actually a novel process we published on, which has, as we talked about, these three components, which is the magnet, the hydrogel backpack for drug delivery, and then the driller itself. We use 2-photon lithography. And here we can see our actuation control. This is just within a agar gel, which is a reasonable phantom or substitute for brain tissue, so that you can see the complex trajectories which we are able to control our nonlinear movement. Of course, nonlinear movement is one of the major applications of this technology. Here we're spelling out GT because my good collaborators from Georgia Tech. And you can see here the sort of speeds and complex shapes we're able to do. And then you can see, of course, on the other video, how the differences in speed at this scale, when you add something as relatively small as a small hydrogel backpack to be able to carry your drug, how that greatly affects your performance speed. And this is some of our data. So our current lead application for this particular talk deals with potentially a pH-sensitive targeted payload or for drug delivery or some therapeutic delivery, depending. And so in this case, the surgeon creates a tiny burr hole in your, testing, preclinical testing system of interest, less than 1 millimeter. And for this demonstration and graphic, we just included one, but obviously this is a swarm technology. We then get our microbots to go to our desired location, of course, bypassing functional tissue with any nonlinear path that you would like to do as powered by your 3D magnetic fields within your imaging system. It goes therefore then to the tumor. It can be obviously in very deep locations, which is the best application for this. And in this particular case, that backpack is made out of pH-sensitive hydrogel, which then expands when it moves into a difference in pH, particularly within the tumor. This allows the nanoparticles which carry the drug to be released in a selective manner. Then, of course, the microbot and the swarm of them can be taken out through the same trajectory or any trajectory you want with minimal damage and retrieved from the brain. And so obviously people want to see, is that actually feasible and possible? So this is us using that pH sensitive payload delivery for our targeted a change in pH. And you can see here, this is the hydrogel backpack using fluorescence markers. You can see that after 50 seconds, there has been selective release of the nanoparticles in the top in the pH of 6.2, which is where the tumor is supposedly, and then at pH 7.8, which is normal brain tissue, you see that very little of the fluorescence has been delivered. Obviously, this is not the only application of this technology, but it is one that we have worked on significantly just because it was some low-hanging fruit. The next aspects of the platform technology is, of course, actuation and control, so more from an engineering perspective. And for this, obviously, you would think, well, how do you actually keep in track of something that's so small? I mean, it's very hard to see from a, from your vision and just from eye standpoint. And so in order to do that, we need some special imaging, not just CT imaging. Obviously, the resolution of CT is too small, and MRI is not really feasible because we're using magnetic fields to guide these things. And so across the field in medical microrobotics, they use a lot of fluoroscopy, but even that is not a very good way to track, at least as you know, within the brain, the trajectories at the precision that we need. And so instead, we use something called photon counting CT, which has increased ability, spatial resolution, decreased signal to noise issues, and then we are able to distinguish between different types of material with photon counting CT. And so we actually have a specific research setup with one of our collaborators at Emory, Dr. Portameza. He's an imaging specialist, and we have a new state-of-the-art Siemens technology to be able to build this clinical system, which we're doing right now. And so first we started by obviously optimizing in the setting of CT our magnetic coils for human integration. And then, of course, we use machine learning to be able to do that. So in this case, and this is some about to be published data, we use some particle swarm optimization. And of course, as you can see here, a neural network to be able to identify our best configuration, which interestingly, compared to the rest of the field in medical microrobotics, is not clustered around the patient, but actually is more of a planar configuration. And then here's some early preliminary data, which shows just in a phantom we are, as you can see, these are very tiny devices. And so to be able to identify them, to track them, and to be able to orient them, because obviously the orientation makes a big deal. We have developed a way to be able to put metal markers on there of two different metals. And you can see here, there's because of the spectral CT or the photon counting CT, we can actually delineate the difference between those two metal markers to be able to tell how the microbi is oriented, which doesn't sound super exciting, but actually is a very challenging thing to do. And so obviously this is a platform technology. We talked about drug delivery, but we are also working on other applications as well, such as microsensors to be able to tell, normal versus abnormal tissue pressure, all those kinds of things. Biopsy is obviously another low-hanging fruit application, neurostimulation. And obviously the goal is one day to be able to get to something as complex as microsurgery, but obviously a lot of work needed before then. And so here's some of our just published data on our microsensors that we have developed for a slightly different application, but also applicable here. We tested this in a pilot study for high-grade glioma, but these are microelectromechanical sensors. These are just small sensors that are able to give you a very quantitative electrothermal or mechanical signature for whatever you're interested in probing. And so obviously we have many ways of being able to tell subjectively what is tumor or not tumor, like fluorescence or imaging, but quantitatively it's actually very hard. And so that was our goal. This is obviously a goal of our group for a lot of applications, sometimes for microbots, but other things like automated tumor resection and robotics in general. And so this project was born out of this. And this is with Dr. Jada Desai, also at Georgia Tech. And here we developed these microsensors that actually are able to measure nanoforces. And we put this on the edge of a robotic arm or a steerable robot, as you can see here, just so we could probe around the cavity, a potential tumor cavity with some control. And we tested this in 6 different high-grade glioma specimens, as you can see here. And you can see actually very reliable ability to tell what is normal, right? Pathologically normal versus, or at least infiltrating tissue versus pathologic tissue. And so obviously the integration of that into our microrobotics is one of our next steps, but a good example of another application. And so obviously many areas of further investigation. It's a whole technology to develop and actually a whole field that's very active within the medical microrobotics community. I always say it's good to have a sanity check when you present things because my partner always says this is my science fiction project. And it's been a real pleasure to be able to talk to you about some of our research. These are our funding sources and our wonderful collaborators at Emory and at Georgia Tech, for which we could not do this work. We are on PBS if you want to check us out this fall, and we're happy to take any questions.
Thank you. Fantastic work. We have time for a question or comment. In the back there.
Thank you for the talk. Super interesting. I was wondering, when it comes to the swarm technology at kind of such a small scale, if it's in the brain, if there's anything that you can, any study of what to do when a group of the swarm is in a place where it shouldn't be, is there a way to kind of sync them back up, or is it a study being done on movement, fine movement of such a small scale of robotics?
Yeah, I think that actually leads to a really interesting area, which I didn't want to cover because there's only so much time. But at this scale, you're like, well, how do you get one robot to do one thing? Like, let's say it got lost, one of them got lost, and the group of them is doing fine. Or can you get, if they're truly going to be working cooperatively together, can you have some that do biopsy and some that do payload delivery together, or working together to do microsurgery, right? And that's actually a whole subsection of microbots, has to do with something called step out frequency. So if you design at this scale microrobotics that are slightly different in their design, shape, size, those kinds of things, the amount of electrical field that you give can specifically actuate one robot versus another very selectively. And obviously, and that's some unpublished work, so I didn't want to include all of it, but that is actually a very good question and an area of research. Yeah.
Thank you.
Well,
Okay, one more question.
That actually answered a little bit of my question. So I guess I'll have to come up with something on the spot. But
Okay.
by the way, a really incredible presentation, and this really is science fiction coming to reality. But one of the things that I was going to ask was this payload, just how concentrated is the payload in each one of these individual microbots? And is there ever a implication with toxicity if it does need to be highly concentrated in particular areas?
Yeah, so obviously the microbot is it's completely scalable depending on payload. And whenever I go to talks about payload delivery or targeted drug delivery, my first question to every presenter is like, how much volume of your targeted substance, whether it's gene therapy or chemotherapy or immunotherapy or whatever it happens to be, do you need? And actually, a lot of researchers don't know the answer to that question. When I ask them, like, how many microliters do you need to deliver? Because obviously that would affect how much we can, how big we need to make our microbots, that backpack, how much would we need to pack with nanoparticles and those kinds. And nanoparticles doesn't have to be the only way that you deliver something. And so I think that is highly scalable, which is the nice thing about being able to 3D print the microbots. You can scale your technology quite easily, actually, to whatever the application is for wherever you want to deliver it.